We've learned that sustainability can be affected in a variety of ways. We can make changes anywhere in the materials economy process towards securing our future survival. Engineering is an integral part of the materials economy and certainly an enabler of the faulty process that it is. But engineering is also being implemented in sustainability solutions, particularly in the area of thermodynamics. I hope to show my thermodynamics students that quantitative analysis will show the sustainability of certain alternatives. Now, thermodynamics deals with studying the transfer of energy to and from pure substances that undergo phase change, for example, water or refrigerant. Two processes in particular that we analyze are 1, the air conditioning system, and 2, the heat pump system, the latter being the system to heat living space. These two systems normally use electricity to run, and as everyone knows, using electricity generates carbon footprint. An air conditioner makes a space cool by transferring energy from the space at the cost of increasing the energy of the outside air, thereby heating the outside air. Normally, you cool a house when it is hot outside, so you are working against the equilibrium state of the outside air by trying to heat it. This takes energy. A heat pump simply reverses the air conditioning process by dumping heat in the interior space, cooling the outside air. Normally, you heat a house when it is cold outside, so it takes energy to work against the natural equilibrium state of the outside air by trying to make it colder. The energy transfer of those two systems can be designed to take advantage of what is called ground source. For an air conditioner, the heat can be dumped to something cooler than the hot air, such as a body of water. The same body of water can be used for a heat pump if the source is warmer than the cold air. An alternative heat source for a heat pump could be geothermal. Either way, using ground source takes up less electrical energy, therefore generates less carbon footprint. The R building uses ground source for heat and cooling. Traditionally, thermo students by the end of the course will have the capability to calculate electrical energy required in kilowatt hours to operate an air conditioning system and a heat pump system. Students are given operating parameters such as desired building temperature and building energy heat loss. It will be a small additional step for them to find how to calculate carbon footprint. They will then analyze the heat pump and air conditioner, except with those systems using ground source, provided with applicable parameters. Their calculations will clearly reveal to them that ground source systems generate less carbon footprint. Arriving at this realization on their own should leave a greater impression. Luckily, the text I use has good candidate problems that I can modify for this sustainability exercise, which the students will be doing as homework. Here is a sample air conditioning problem. This particular problem is actually for a smaller volume, but illustrates the parameters that need to be provided for a student to solve. Here is a sample air conditioning problem where ground source is used. Again, this is for a smaller volume. Here's a sample heat pump problem. This problem is more appropriate for the stated goals. The COP, or the coefficient of performance, can be used to derive energy required to run the heat pump. Here's a sample heat pump problem where ground source is used. This one is really appropriate and will be used as a basis for the traditional heat pump problem. One option I'm entertaining is getting parameters that approximate those from the R building. If I do this, then the students would have the opportunity to have made similar engineering calculations in deciding to integrate ground source in the R building. This, combined with an optional tour of the R building, should really drive the point home.